Mm. Okay, it looks like it's recording then. So
Yeah, it is.
great, thank you. Sorry for doing that. My iPad will take up all the memory. So let's get started with today's class. Maybe before we do anything related to chapter 7 that we were on, do you have any questions related to maybe tomorrow's test or anything that have come up that you want to ask?
Yes. How long will it last?
I think it's 2 hours.
Okay, thanks.
You're welcome. Is there still an internet problem on the campus?
Normally there shouldn't be. We got an email. I mean, I'm not on campus, but we got an email saying that it was fine now, and most
Okay.
people were in the class this morning. But do you know why we have a 3-hour slot for the test tomorrow?
Oh, yeah, no, the reason why it appears as 3 hours on the timetable is just that Anthony put 3 hours, and whenever I've got to add a third of the time on anyway to for the tiercent, so it's 2 hours for sort of normal people. The normal test length is 2 hours, and then if you have a tiercent, it's 2 hours 40, and it was just easier to block out 3 hours.
Okay, thank you.
You're welcome. So yeah, it'll be 2 hours in the same the same organization as last time. So with the same thing on Moodle, and yeah, that's how it will work. If you don't have any sort of maths questions, what we can do is just do some more work on chapter 7 that we've almost actually finished.
I have a question.
Yeah, go on.
When I want to do the limit at plus infinity of a rational function, are we allowed to use the fact that we can take the limit of the larger degree? I don't know how to explain that.
Yeah, no, I see what you mean. If, for example, yeah, I think I see what you mean. If you have, say, I don't know, x5 plus 2x3 divided by x4 plus, I don't know, x2, that's not a rational function, but it's a limit of polynomials anyway. What you can do with the knowledge that you have now is say that at plus infinity, it goes to plus infinity because you've got this thing that takes out, wait a minute, where is it? This thing at the top.
Your screen. Yes.
Oh, sorry. I'm not quite awake. Partager. That will work better. Okay. Hopefully you'll be able to see it in a minute. So if we take this, can you see my screen now?
Yeah, that's fine, thanks.
Okay, so if you've got a ratio of polynomials, so it sort of generalizes to rational functions. This, for example, if you wanted to prove it properly, I guess you could factorize by x at the top and the bottom, or factorize by x5. You get 1 plus 2x2. Probably the same on the bottom, and you could write the limit neatly, but you can just give the limit of that directly nowadays. You don't have to write as much as you did at Lycée, if that's what the question is.
So we don't have to factorize, we can say directly.
No, yeah, exactly. Yeah,
Okay.
you just need to compare the degree terms, the degrees of the various terms, as you were saying, and be careful if there are any coefficients in front there. But yeah, that's how you can. You're welcome.
I have a question too.
Yeah.
If we are trying to compute the limit at A of the ratio of two functions f and g who are differentiable on a neighborhood of A, can we use the ratio of the derivatives to compute the limit?
So you want to do, you're looking at that, for example. Is that right? And you want to use the ratio of the derivative. You want to use L'Hopital's rule or something.
Yes. Are we allowed to use it?
Normally, yeah, I think if you know it, you can use it. But have you seen that in previous years?
Well, no, but when I was studying, I saw it, and So yeah.
Okay. Yeah, no, you if you know how to use it properly, I'd say yeah. But I think we're going to see it a bit later in the week, L'Hopital's rule, and it's something you'll see in the second semester as well. If you know how to justify things, then yeah. Yeah. Are there any other questions? Yeah, if any come up, you don't hesitate to ask them. If in the meantime, what we can look at is the inverse of cosine. So if we look at the exercise sheet, we've got the inverse of cosine left. We've got the inverse of arctangent, or tangent, the inverse of hyperbolic tangent, sorry. And we've got some equalities to prove. And that will be it for the part on continuity theorems, and then there'll be some stuff on differentiability, including here L'Hopital's rule. But so we've got a few exercises left, but we've almost finished them for this chapter. So let's have a look at the inverse of cosine. So I'm going to go quite quickly on this exercise. Well, I'll justify things, but probably go a little quicker because it's exactly the same structure as what we did for sine. So if you've got your notes from last week, you'll see that the questions that we answered for arc sine are exactly these questions. So we just need to adapt things to cosine, but the reasoning will be roughly the same. So what we're going to do in this exercise is define the inverse of cosine, which will be arc cosine. And what we're going to do that is take cosine and restrict ourselves to an interval 0, pi. And that's going to allow us to define our inverse. And so what we want to do is to prove that we've got a bijection when we restrict cosine to 0, pi. So what elements do we need if we want to prove that we've got a bijection?
It has to be strictly increasing or strictly decreasing on an interval.
Yeah, absolutely. So that's the first thing. We need some sort of strict monotony. And there's one other element that we need. Can you find a bijection? Can you always find a bijection if you're not continuous, or can you apply the theorem that we have if we're not continuous?
No. No,
exactly. So we need continuity as well as strict monotony. So let's have a look at that. So if we take a look at G that we've defined above, or H rather, H is continuous on 0, pi. Okay, that's the first thing. As cosine is basically C infinite on R. In particular, if you just restrict it to an interval, you'll get a continuous function. It's even C infinite on 0, pi. What about increasing or decreasing? What property holds for this function? So if we take,
it's decreasing.
Yeah, absolutely. So if we look at 0, pi without the edges, we've got cosine of x. So cosine prime of x is equal to minus sine of x. And that's strictly smaller than 0. So if we just use the last point, we've got cosine is decreasing on 0, pi. Okay, that's using the theorems that I think we re-mentioned them at the end of the chapter 7. So cosine is decreasing on 0 pi, and that's sort of a strict decreasing. And we can deduce, wait a minute, that's H. H is a bijection. Bijection from 0 pi. We need to find the image set. So how would you get the image set for this function?
We know that it is strictly decreasing, so if we just take the borders and calculate the cosine of it, we will have the borders of the image.
Absolutely, yeah. Just got to be careful because it's decreasing. So cosine of pi, you should get -1, and cosine of 0, you get 1. So we'll get a bijection from 0 pi to the image interval. And so the interval that's k above here is -1, 1. And so as a consequence, we can define arc cosine. Which will map from -1, 1 to 0 pi. Okay, so we've got a bijective function, and so we can define its inverse. And now we're going to have a look at some properties of the inverse function. So the first thing that we're going to do, like we did for sine, is we're going to compute some values of the of arc cosine. So we want to find arc cosine of 0. So if you want to find arc cosine of 0, you need to find a value between 0 or between 0 and pi, sorry, such that if you take cosine of that value, you'll get 0. So if we try and apply that, we should have, if you think of the trig circle, for example, you see that cosine of pi over 2 is equal to 0, and pi over 2 belongs to 0 pi. So arc cosine of 0 is equal to pi over 2. And reasoning in a similar manner, you will get arc cosine of square root of 3 over 2. That's equal to pi over 6, okay, because cosine of pi over 6 is square root of 3 over 2, and pi over 6 belongs to the interval 0 pi, and arc cosine of 1 is equal to 0. So those are 3 specific values, and then if we take a look at the last part of this question, we want arc cosine of 15 pi over 4. What do you think that's equal to?
Three over 4.
Said minus pi over 4.
I think.
Oh, sorry, never mind. Yeah, no.
You've both got the right idea, but it's actually none of the two. But you've both got the right idea. So if we have a look at how we can do this, if we take cosine of 15 pi over 4, what we can do is remove 2 pi increments, right? So that will be equal to cosine of minus pi over 4. Because you are removing 16 pi over 4 to get that, which is a 2 pi increment. And that's what we did for sine, I think. We ended up with minus pi over 4 in this case, and minus pi over 4 is in the right set. But here, minus pi over 4 doesn't belong to 0 pi. But the problem is, if you add 2 pi to this, you'll be outside of 0 pi again. But we can use one of the parity properties of cosine, or the parity property of cosine, to write that this is equal to something else.
It's also equal to cosine of pi over 4.
Absolutely, yeah. Yeah. So this here is just using the fact that you can remove 16 pi over 4, and that's because cosine is an even function. So you've got cosine of minus x equal to cosine of x. So what does that tell us about the value that we're trying to compute? So arc cosine of 15 pi over 4.
It is pi over 4.
Yeah, absolutely. It will get pi over 4, and we can do that as pi over 4 belongs to 0 pi. So that allows us to deal with the last value that we're asked to compute. Okay, so those are some values. And then what we're going to look at is what happens if you apply cosine to arc cosine and arc cosine to cosine. So we're going to look at in which setting we get the identity function or not, or in what sets we get the identity function when we take these applications. So the first one I think is cosine. If I move up, it's cosine applied to arc cosine. So if we have a look at cosine applied to arc cosine, so the first thing that we do if we take that application is we take arc cosine. So arc cosine maps from 1, 1, as we defined it above, to 0 pi. Arc cosine. And where does cosine then map to? If you apply cosine to 0 pi?
Again to minus 1, 1.
Absolutely, yeah. So that's what happens if you look at these sort of image sets when you apply these two functions successively. So where do you think cosine of arc cosine of x is equal to x at? So we want cosine of arc cosine of x to be equal to x. What sort of set should I put here?
Minus 1, 1, the definition domain of
Yeah.
arc, of course.
Yeah, absolutely. Basically, there's nothing that goes wrong when you apply these two successively, because arc cosine to start with, you can't work with arc cosine on R. You restrict where you work to minus 1, 1, and you get the identity function. So if you look at the question, I think you want to look at where that's a set G where cosine of arc cosine is equal to the identity function. So what we have for any G included in minus 1, 1, cosine of arc cosine is equal to the identity function of the set G. Okay, so that's the first application. And now we're going to look at what happens if we write things the other way around. So if we first apply cosine takes its values in R, and then from R it will give you something in minus 1, 1, and then so that's cosine. And if we apply arc cosine now, you'll get something that goes from minus 1, 1 to 0 pi. So where are you going to start to recover your initial value if you're applying cosine of x and then arc cosine of x?
Only from 0 to pi.
Absolutely, yeah. So if you work with 0 pi, then arc cosine of cosine of x will be equal to x. So if we want to think it's find h such that arc cosine of cosine is equal to ID of h, we have to take some h included in 0 pi and not in the whole of R. That's sort of what was illustrated in the example above where we had 15 pi over 4. So once again, this is an example where you've got to be careful with inverse functions because sometimes you have to restrict the definition domains to define the inverse, and then some strange things happen if you apply the inverse functions in the sort of wrong order. So yeah, arc cosine of cosine, you got to work with 0 pi if you want to define, if you want to recover the identity function. Now, if we take a look at the next question, I think if it's like sine, yeah, which it is, we're actually going to study arc cosine of cosine now, and we're going to study it on R. And so we're going to build on this to try and trace the function on the whole of R. So we want to graph a function that maps x to arc cosine of cosine of x. Okay, that's the thing that we want to do, and above we know that it's equal to the identity function on 0 pi, and then we need to work a little bit more regarding this function. So there are two ways of doing this. Maybe the first thing we can have a look at is whether the function is periodic. So do you think this function is periodic?
Yeah.
No, because it's. Sorry, I think someone else was speaking. I think it's not periodic because it's strictly decreasing, and it's continuous.
Okay, that's
I agree, but on the whole of the definition domain, it has to be because cosine is periodic. So with a repeating cosine value, our cosine can only map to one thing.
Yeah, that's quite a good way of putting it. So the answer is that it is periodic, with cosine being periodic. So we'll be able to prove it. And the fact that it's decreasing, if we have a look, we know that basically cosine is decreasing on the definition domain that we consider for the inverse. But what we're looking at here is arc cosine of cosine, where cosine can map with x on R. And so we don't know whether it's going to be, how can I put it? Cosine of x is going to fluctuate periodically, and then we're going to apply arc cosine to it. So the fact that it's decreasing just on certain part doesn't tell us about the behavior on the whole part of R. But if we want to look at the periodicity, what we can say is that for any x on R, x plus 2 pi belongs to R, and cosine of x is equal to cosine of x plus 2 pi. And now if we apply arc cosine, and that will belong to minus 1, and so if we apply arc cosine on either side, we get this. We get arc cosine of cosine of x plus 2 pi. Okay, so it's purely down to the periodicity of the cosine function, that this function is periodic. So x maps to arc cosine of cosine of x is 2 pi periodic. So that's the first thing that we can note, and we already know the behavior of this function on a pi length interval here. We know that on 0 pi, arc cosine of cosine is the identity function. Can you see any other property for this function? For example, parity properties?
It is even because cosine is even.
Absolutely, yeah. That's the thing that we used above, still with 15 pi over 4, when we went from minus pi over 4 to pi over 4. So what we have is the following. We have cosine of x equal to cosine of minus x, which in turn belongs to minus 1, 1. And so what that means is arc cosine of x is equal to arc cosine of minus x. And so our function, arc cosine of x is even. So we know it's 2 pi periodic, it's an even function, and if we take x on 0 pi, arc cosine of x is equal to x. So do we have enough information to graph this function now? The answer is yes, because as it's even, you know that on minus pi 0, it'll be equal to, you'll have the value for minus x equal to the value for x. So you'll have some sort of symmetry around 0, and then you've got a pattern for a 2 pi length interval that just repeats because you're 2 pi periodic. So we can graph the function and you'll get something that's got some similarity with what we had for sine. So if I put pi here, minus pi, and pi here, you'll get this, and you'll continue that pattern. Yeah, you've got some sort of repeating triangular type motif. So that's roughly the curve of cosine of, of arc cosine of cosine. Okay, let me just take this. So we've graphed arc cosine of cosine. What we're going to do now is look at the actual properties of arc cosine itself. So the first thing that we're going to do is have a look at whether arc cosine is decreasing and continuous. What do you think about that? How can you prove it?
think the inverse function have the also decreasing if the function, I mean, cosine is decreasing.
Yeah.
So arc cosine should also be decreasing.
Absolutely, yeah. So the fact that cosine is decreasing and cosine is continuous just gives us the fact that arc cosine is decreasing and continuous on their definition domains. So let's have a look at that. So G, the restriction of cosine to the intervals that we're interested in, that I keep calling G but is actually H. H is continuous and decreasing.
If we get the inverse of a function, it has the same monotos, I don't know that name.
Yeah.
Okay, and what about the convexity or concavity? Is it reversed?
That's a good question. Let me think.
I think it is, because it's like a symmetry with the
I don't know if it's a good enough proof.
Let me see. One way, yeah, it probably is, because if you take x squared, you'd get, for example, x squared and square root of x are an example where it works. Logarithm and exponential as well. There probably is a way of, well, there will be a way of proving it. I think it probably is if you have concave or convex on an interval, for example, or on a set, then it probably does translate quite well. I guess if you get changes in concavity and convexity, it's probably more awkward to prove, I'd guess. But when you're graphing functions and you want to graph their inverse functions, for example, if you want to just inverse x squared with x squared convex, this isn't a proof, but you can see that the inflection of x squared sort of translates the other way around onto a square root of x. And I think you could probably have a look at the second derivatives, because you could probably compute the second derivative of your inverse function and prove things like that, I'm guessing. But it's a good question to ask. It's not something that we have as a sort of result yet. But yeah, there we go. So H is continuous and decreasing so H was defined on 0 pi. So arc cosine, continuous and decreasing. And that would be on -1, 1. Now, what do you think about functions that are even? For example, you know that cosine is even. What do you think about arc cosine? Do you think that property can translate to the inverse?
No, because we only take a restriction of cosine, not a whole cosine graph.
Yeah, absolutely. The function being odd can translate to the inverse, but even not. In fact, as soon as the function's even, you've got to restrict, as you were saying, the interval that you consider to somewhere where it's not actually even to get a bijection. So no, and even the fact that a function is even does not translate to the inverse function. So that's one thing to watch out for. But yeah, we've got decreasing and continuous, and we're going to look at differentiability. So how can you deal with differentiability?
If cosine is differentiable, and if not, and the differential, the derivative isn't equal to 0, then it's also differentiable.
Yeah, absolutely. So as soon as the initial function is differentiable, the inverse will be, as long as the value of the derivative is not equal to 0. So let's have a look. So H for any x, let's have a look at where the derivative has a the initial function has a derivative equal to 0. So if we take x on 0 pi, h prime of x is minus sine of x. And so minus sine of x equal to 0, that's equivalent to sine of x equal to 0. And where do we have sine of x equal to 0 on 0 pi?
when x equal to 0 or pi?
Absolutely, yeah, when x is equal to 0 or pi. So if we take the restriction for x belonging to the interval 0 pi, sine of x is equal to 0 at the sort of edges of that interval. And what that implied, or what that followed from, was the fact that h is differentiable on the interval 0 pi. So if you work on 0 pi, h is differentiable, h prime is minus sine of x. And that's different from 0 except at the edges of the interval. So if you use the inversion theorem, arc sine is, or arc cosine rather, x maps to arc cosine of x is differentiable on minus 1, 1, from which we remove cosine of 0 and cosine of pi. So what do we get if we remove cosine of 0 and cosine of pi from the interval minus 1, 1?
We open the interval.
Absolutely, yeah. This here is minus 1. 1, so your differential everywhere except at the edge. So that proves differentiability. And we get the image, the sort of set that we wanted to for differentiability. And we need to prove the derivative. So if we take x on minus 1, 1, we can compute arc cosine. Yeah, go.
Sorry, I didn't really understand why we remove cos of 0 and cos of pi to the differentiability domain.
Okay, let's have a look at the inversion theorem. So let me just get that. There are two ways of answering that question. Where is the inversion theorem? It's around here. Okay, the first way of answering it is that basically, if you take a look at the theorem related to the inverse of a function, if you get differentiability, imagine that you were able to differentiate your inverse. You end up with 1 divided by the derivative of your initial function at a certain point. And so if you have 0 here, then your this thing isn't well defined. You get 1 over 0, this thing explodes, and so your derivative doesn't really exist. The other way of looking at it is that if you take a certain function, for example, if you take x squared and square root of x, basically when you take the slopes of your functions, so that would be, this function is roughly the inverse of that function, and so anywhere where the slope here is equal to 0 becomes a vertical slope when you look at the inverse function. So a flat slope here becomes vertical, and you know that sort of roughly when you have a vertical slope is in a sort of an area where you don't have differentiability. So when you sort of when you draw the inverse of your function, anything that's flat becomes vertical and you lose differentiability. So you've got to remove those points from the place that you are deriving at. So the idea is that you need to check, you take the definition domain of your initial function f, and you're going to check where that function has a derivative equal to 0. And then you need to remove the images of all those points. So f of x0, you need to remove them from the differentiability domain, because otherwise you'll end up with issues related to the slopes that you're working with. So here we had 0 and pi as the areas where cosine prime equal to 0. And so you take your arc cosine will be differentiable on its definition domain minus the image of those places. Does that answer your question?
Yes, thank you.
You're welcome. So if we now try and compute the derivative, what we get if you apply the formulae from the notes, you get 1 over f prime, where f here was the cosine function, so you end up with minus sine. And you're going to apply minus sine of x to arc cosine. Okay, and we want to rewrite that in another way. So we can put the minus sign up top if we want, and we could just need to deal with sine of arc cosine of x. And how can we rewrite this? So we say
by
x.
transforming sine of arc cos of x with square root of sine squared, because arc cos gives value between 0 and pi, and there sine is positive.
Absolutely, yeah. We're going to use the sort of usual trick, using the fact that sine of x is positive and 0 on 0 pi, and this will belong to it will belong to the open interval, like this, and like that. So what we can do by noting the fact that we've got some positivity is rewrite this as minus 1 divided by the square root of sine squared applied to arc cosine, and apply our usual trick then of using the fact that sine squared plus cosine squared is equal to 1. So this is minus 1 divided by what would it be, 1 minus, so you get sine squared plus cosine squared equal to 1. So that would be 1 minus cosine squared applied to arc cosine of x. And once we reach that, we can just rewrite things as minus 1 divided by square root of 1 minus x squared. And that's the formula that we wanted. So that gives us the derivative. What's this derivative equal to at 0?
1. X is equal to 1.
Yeah, you get minus 1. But yeah, you get if you look at the tangent around 0, you get sort of a slope roughly equal to minus 1. So what we can do is use this behavior to give a rough graph of the function. And I think that's the last question. So it's question 7. And it looks something vaguely like this. So you get 1 and minus 1. Now we'll get, maybe if I need to put them a bit more symmetric. We'll get 0 and say pi. And so we're equal to 0 at 1 with a vertical tangent. And we'll be around here at minus 1. And we'll have a vertical tangent too. You get something roughly like that, but that's not the best curve. Yeah. my curves are never that great, but that's the rough behavior of the function. And if I might be able to screenshot a better curve during the break in a minute, at 1/4 and then you'll get a better graph of it. If you type arc cosine on Google, it'll give you a better graph than the one that I've drawn, but that's the rough behavior of arc cosine. It's decreasing in particular, and it's not differentiable at -1 and 1. Okay, are there any questions?
I don't have any.
Okay, yeah. If there aren't any, we can have a look at the final function that we're going to inverse, which is the hyperbolic tangent. And we can do some questions related to the inverse of that function. And it's something that you'll find in, I think, exercise 8. Yeah. So let's have a look at that. So can you remember how the hyperbolic tangent is defined?
Wasn't it hyperbolic sine over hyperbolic cosine?
Yeah, absolutely. Hyperbolic tangent is the same principle as normal tangent. So it's x maps to hyperbolic tangent of x, and that's sh of x divided by ch of x. And if you want to go further and write expressions with the exponentials, you get the following. You get the difference of the two exponentials. So exponential of x minus exponential minus x divided by the sum of the two terms. So that's hyperbolic tangent, and we're going to look at inversing it. So can you remember where that function is defined continuous differentiable?
Defined on R. Differentiable.
Yeah, absolutely.
Also on R.
Yeah, absolutely. Sorry?
What was the other question?
Continuous, but as you said, differentiable. You've sort of you've answered it. That's great. So the key thing here is that the function is basically made up of exponential functions, and the denominator here will never be equal to 0, as you've got a sum of two exponentials. So what you can say is that G3 is defined continuous and differentiable on R. Okay, and if we look for the derivative of the function, so we can study the monotony and see whether we have a bijection, we get the derivative equal to, if you use this expression, using the fact that sh prime is ch and ch prime is sh, you'll get ch squared of x minus sh squared divided by ch squared. Okay, this is a calculation that we did, I think, in chapter 5 or 6, and you get 1 divided by ch squared, and a further calculation that we did is that that's equal to 1 minus th squared of x. But we can even stop here if we want the sign of the derivative. What do you know about the sign or the values of ch?
They are greater than 1.
Yeah, absolutely. So they're greater than 1, so there's no problem here dividing by 0. That's the first thing. So what can you say about the sign of this term here?
It is positive.
It is always positive.
Yeah, absolutely. If you take any x in R, G3 prime of x will be strictly greater than 0. if you take some big value x, you'll possibly be quite close to 0, but you'll never actually reach 0 for a fixed value in R. So G3 is strictly increasing on R. Okay, so what can we say now about about G3? Is it a bijection?
No, it is even, so it can't be a bijection because ch of x is even, so ch squared of x is also even, and even if we divide it by it, it's still even.
You're right about so that is even, yeah, but that's a derivative.
Oh yeah, sorry.
Yeah, no, you're absolutely right for that function. And yeah, that's even. But what we're looking at is this one here, and what we've seen is that it's continuous and strictly increasing. So that should tell us that it is a bijection. And it takes its values in R, and what we want to determine is the sort of the image set. So we need to look at the values of the function at plus and minus infinity. So if we take a look at th of x at plus infinity, can you remember what value you get? And the limit at minus infinity.
For plus infinity, we get plus infinity, and for minus infinity, we get minus infinity.
Yeah.
Not quite.
1 for plus infinity and -1 for minus infinity.
Yeah, absolutely. Thanks. Yeah, here each time there's, if you look at so for example at plus infinity, this goes to 0, this goes to 0, this goes to plus infinity, and this does too. So it's a sort of indeterminate limit, but if you factorize by exponential of x, then you'll see that you get something that goes to 1 and the other terms go to 0. And similarly for minus infinity, it's these terms that take over and those will go to 0. So yeah, we have these two limits. So you've got 1 and -1. And so what does that tell us about the image set of TH?
We could say it's inversible for -1, 1, for y's belonging to that -1, 1 range.
Yeah, absolutely. So what we can say is that, so what we can sort of conclude that G3 is a bijection from R, which is where it takes its values, to -1, 1. And we define its inverse. So it's argth. And as was just said, it goes from -1, 1, that's where it takes its values, and it goes to R. So we can inverse the hyperbolic tangent. So that's the first thing. In the second question, what we're going to look at is the parity of argth, and we're going to look at the limits at the bounds of the interval. So we've almost answered the question related to the limits here, to be honest. But we can have a look at the parity. So what do you think about the parity of the parity of the hyperbolic tangent?
It's odd.
Yeah, absolutely. So TH is odd. So argth is also odd. So that answers the sort of first part of question 2. And in the second part, we want to look at the limits of argth at the bounds of the function. So we want to look at the limits of argth at -1 and 1. And we can deduce them from the limits for th. So if I put 1 and say -1, or plus infinity, sorry. So you know that th goes to 1 at plus infinity. So what can you deduce for the inverse function from that?
That for y going to 1, we have the limit that is equal to plus infinity.
Absolutely, yeah. You just need to switch the bounds of the limits to get the behavior of the inverse function. And so you get plus infinity at 1. And so equally, we can have a look at the other limit that bounds. So at minus infinity, th goes to -1. And so if we use the same principle, we can get the limit of argth at -1. And so we'll get minus infinity. There we go. Now, that's some information about argth. And we can go further and look at the differentiability of the function. So is th differentiable? And is the derivative ever equal to 0? In fact, I think it's written, so it's written above that th is differentiable on R. So th is differentiable on R. And for any x on R, is the derivative of th ever equal to 0? So we get 1 over the square of the hyperbolic cosine, which is up there. So you get
No.
1 over, yeah. So you get 1 over ch squared of x, and you get something that's strictly positive. In particular, that's different from 0. So what can you deduce about where argth is differentiable?
It is differentiable on -1, 1.
Yeah, absolutely. So argth is differentiable on -1, 1. And we can compute the derivative. So for any y belonging to -1, 1, argth prime of y is equal to 1 over th prime applied to argth of y. Okay, that's the formula. And the thing that I'm going to do here is use this formula for the derivative that we proved in chapter 5 or 6, wherever we defined hyperbolic tangent. So you get 1 minus th squared. And that helps us compute a nice expression for the derivative. So you get th of squared applied to argth. And so we should end up with 1 divided by 1 minus y squared. And so again, you get this derivative is another one that can be useful when computing primitives of certain functions. So it's another formula that you can add to your sort of grid with all of the reference functions. This one, in fact, and arg cosine that we just did. Now, we saw with the two other hyperbolic trig functions that the inverses have explicit expressions, and argth is no exception. In fact, it's quite possibly one of the easiest ones to compute an explicit expression for. And so we're going to do that here to finish this exercise. And so what we're going to do is let some x in -1, 1. And we're going to say that argth of x is equal to c. And we're going to try and get an expression for c. Okay, that's our aim. We fix x, which is some given data, and we want some sort of expression for c that's perhaps more explicit than just being the inverse of the hyperbolic tangent function. So how can we rewrite this equation here? So if you apply hyperbolic tangent to both sides, you'll get this equality. And if we apply the formula for hyperbolic tangent, we get this. So exponential of c minus exponential minus c divided by exponential c plus exponential minus c. So that's just the formula for hyperbolic tangent is equal to x. Now what can you do here to sort of simplify this equation or rewrite it?
We can apply ln.
You can apply ln. The problem is you apply ln, you'll get a difference of two logarithmic terms here, and you might actually be able to get an expression, but you'll want to apply ln at some point. It might not be the best time.
Maybe we can multiply by e to the c plus e to the minus c, and then multiply again by e to the minus c, and we have an equation with x as a factor. I don't know.
Yeah.
And e to the c is the unknown.
Why not
Yeah,
just find by e to the c?
Go on.
Well, we get e to the c minus 1 over e to the c plus 1, and then we can apply logarithm to the ratio. And we can
Yeah, I think yeah. I think you're on the right path. There are probably actually many ways of doing this. One of them is one that gives you almost the least work. One thing that we can do here is, so there are probably many ways of doing this, but we can bring all the e to the c terms to the same side, so we get x minus 1 as a factor of e to the c, and we'll get exponential minus c. We should get 1 plus x. Oh yeah, no, okay. Yeah, you get minus 1 minus x. You get e to the c. 1 minus x equal to e to minus c. 1 plus x. Okay, that's just rewriting the same equality. And what's nice about this is that if you multiply by e to the c, you get e to the c equal to 1 plus x, 1 minus x. And it allows you to then take the logarithm here. But there are probably many ways of doing it to reach a result. If we do this, we'll get c equal to 1/2 logarithm of 1 plus x divided by 1 minus x. And this, you can check, it's positive between -1 and 1. So arcth of x, that's equal to 1/2 the logarithm of 1 plus x over 1 minus x for any x in the open interval. And you can see that this is quite nicely explicit. If you wanted to do any sort of analysis, it's quite easy then, or even just to draw that function. It's one of the probably the nicest ones to draw. But there we go, that's one way of getting an expression for the inverse. It's probably not the only one. Okay, are there any questions related to the two exercises we've just done?
I don't have any questions.
Okay. Yeah, one thing that you can do at some point is, I think you now know all of these functions, and all of these ones too. So you now know the derivative of all of these inverse functions. So arcsine, arccosine, arctan, arcch, argsh, argsh, arcch, arcth, and you can complete that, fill that in if you want. And all of these are generally of the form 1 over 1 minus x squared, or 1 plus x squared, or a variant of the square root. And you'll see that they can become quite useful when computing certain integrals. So make sure to fill that in when you have a bit of time, because these functions, one of their main uses, one of their times where they are really quite useful is computing integrals, as you'll do, I think, in the last chapter of this semester. But yeah, you can now use all of these inverse functions if you ever need them, and you have we've proven all the properties if you need to refer to them. What we can do now to finish the things with inverse functions is have a look at some equalities. And that's the object of exercise 9, which involves proving a bunch of equalities related to all of these inverse functions. And it can look a little intimidating, I guess, to start with, but there's basically a trick to proving, I think, all of these equalities. They're all based on the same idea, and you will be able to see what that idea is. So in the first equality, we want to have a look at where arctan of x plus arctan of 1 over x is equal to either plus pi over 2 or minus pi over 2. Okay, this thing here is equal to either +1 or -1. Now, if you have either a scientific calculator or a search engine at hand, try and have a look at what arctan of x plus arctan of 1 over x looks like. If you type plot arctan of x plus arctan of 1 over x into Google, it will plot it for you. It'll probably, hopefully, gives you some idea of where we're going with this. What do you see if you plot that function?
I don't know if we can describe it as kind of stairs.
Yeah, that's a very good way of describing it. So I don't look on Safari with my screen, and if I do that, sometimes I lose the zoom thing, so I'll avoid doing that. But I can give you, you should, if you have a look on the internet, if we have a look at the question, if you have a look at the graph of the function that we're looking at in question A, you get something like this. So can you give me a rough idea of the values of which the two sort of stairs are at?
Minus 1.6.
Yeah.
And then 1.6.
Okay,
on
so
the other side of X.
yeah. So if you have a look, you've got, say, two values here. And you've basically got a function that either side of 0 is constant. With one of those values being approximately, so that's approximately 1.6, say, and that's approximately minus 1.6. So that's a rough, if I call, let's say, let f of x, let x map to f of x be equal to arctan of x plus arctan of 1 over x. The graph that's in sort of blue here is roughly C of f. Now, what we want to do in the exercise, in the question that we're asked, is show or have a look at where f of x is equal to minus pi over 2 and where f of x is equal to pi over 2. Now, does that, if you have a look at these values here, are there any that sort of resemble pi over 2 or minus pi over 2? If you bear in mind that pi is roughly 3 and a bit, 314.
These are essentially pi over 2 and minus pi over 2.
Yeah, absolutely. It's, yeah. What we have, in fact, is this. So we have minus pi over 2, and we have pi over 2 here. So if we want to have a look at where these equalities will probably hold, so this isn't a mathematical proof, but if you look at where f of x is equal to pi over 2, what values do you think we should be able to reach? If you want to solve f of x equal to pi over 2, if you look at the graph. You can see here that all of the values to the right hand side of 0, so basically r plus star, you're equal to pi over 2. Again, it's not a proof, but it's what you can sort of get an impression of visually. And if you're on r minus star, you're equal to minus pi over 2. So here, if we have to look for values such are equal to pi over 2, we'll probably get r plus star minus pi over 2, r minus star. So that's what we're going to try and prove. We'll do it after the break. Just before we take the break, what you can see here is you've got a function that's constant here, constant here. How do you think we might be able to prove that the function's constant on either side of 0? If you're working on an interval and you want to prove that a function is constant, what could you do?
We could subtract a constant and prove that it is 0.
Yeah, you can do that. But you've also got the fact that if your function is constant on an interval, it means that its slope is equal to 0. So there's another way of proving that your function's constant.
We show that f of x is equal to f of x over 2.
Yeah, that's another way. Is there not something related to derivatives that you know?
If we take the derivative and the derivative is 0,
yeah,
then it is constant.
Yeah, absolutely. So all of the methods that you've said work, but some will probably be lengthy. For example, first method, so shifting this equation to get something equal to 0. It'll be difficult here because you've got arctan, and it wouldn't really help that much with the equation. The other method, so showing that you're basically, it's another way of showing you're constant, that would work too, but it might be a little bit lengthy. The easiest way to do it here is first show that your function is constant on intervals, and then we'll be able to show that we're equal to either pi over 2 or minus pi over 2. So that's an idea of the method, but we'll do that after the break. So we can take 15 minutes and tackle all of this after the break. So can you still see my screen?
Yes.
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 Great. Okay, so what we just discussed briefly before the break is that if we have a look at the actual graph of the function that's key to the inequality, it's constant on r minus star and constant on r plus star as well. And so we're going to try and use that to solve the equality that's in the actual question we were interested in. So what we're going to look at is the derivative of this function, so f of x. And in order to give the derivative, let's just recall some things related to arctangent. So recall, you should have this in your lecture notes really, but if it's in your lecture notes if you need it. But so you can recall that arctan is C infinite on R, and arctan of x is equal to 1 over 1 plus x squared. Okay, so with that in mind, we can have a look at where this function f is defined and continuous and differentiable. So where do you think it's defined, continuous and differentiable?
Defined on r excluded of 0.
Yeah, so the key is that this part will be C infinite on R, and then this part, so arctan of 1 over x, you just got to be slightly careful because you've got 1 over x. 1 over x isn't defined at 0, but it's defined continuous and differentiable everywhere else. So if you use function composition, you get that f is defined continuous and differentiable on R from which we remove 0. And so if we take x on R star, we can have a look at f prime of x. Okay, so the first part of f, if we derive it, we'll get 1 over 1 plus x squared. And the second part, if we derive it, we need to use composite derivation. And so we'll get 1 over x prime multiplied by 1 over 1 plus, basically we multiply 1 over x prime by the derivative of arctan applied to 1 over x. So we can write it like this rather. We get arctan prime of x applied to 1 over x. So if we rewrite things, 1 over x prime will give us minus 1 over x squared. And then arctan prime applied to 1 over x will give us 1 over 1 plus 1 over x squared. And you'll see that this will simplify. So you get 1 over x squared minus 1 over x squared plus 1. And so that's equal to 0. Okay, so we've got a function whose derivative is equal to 0 at each point of r star. So what can we deduce about the values or the variations of the function that we sort of mentioned before the break?
Well, it seems to be constant.
It's going to be constant, but on each interval where the function is continuous. So one thing we've got to be careful about here, because we see that it jumps at 0. So what we can take away from this is that f is constant on each interval on which the function is continuous. Now, is r star an interval?
No.
Yeah, absolutely. So, got to be careful. R star is not an interval. What about r plus star or r minus star?
They are, yes.
Yeah, absolutely. So r star is not an interval, but r plus star and r minus star are intervals. So what we can deduce from that is the following. For any x on r plus star, so for any x positive, f of x is equal to some c plus, okay, some constant. And for any x that's negative, f of x is equal to some c minus, where c plus, c minus are two real values that we don't know much about yet, and we need to find some values for them. Okay, so what we need to try and do now is try and work out what c plus and c minus are. Now we can, one way of doing this is recalling some limits related to arctangent. So what we want to do is we want to find the values of c plus and c minus. What you can recall is that the limit when x goes to infinity of arctangent of x is equal to pi over 2, and the limit when x goes to minus infinity of arctan of x is equal to minus pi over 2. And we can even recall that arctan of 0 is equal to 0. With arctan continuous at 0. So we've got these three things. And so what we're going to do is we can use these values to find limits of f using function composition. And we can also use these two expressions to find some limits of f at plus and minus infinity. And combining these two approaches, we should be able to deduce values for c plus and c minus. So if you recall that f of x is arctan of x plus arctan of 1 over x, and if you use this lot of information, what can you say about the limit of f of x at plus infinity?
Pi over 2?
Yeah, absolutely. So we can compute some limits. So the limit when x goes to infinity of f of x, that's equal to pi over 2, because we've got arctan of x goes to pi over 2, and arctan of 1 over x goes to arctan of 0, as arctan is continuous at 0, and arctan of 0 is equal to 0. So the pi over 2 comes from the limit that's in purple. And what other value can we deduce for that limit? Using the fact that the function's constant.
All values on our plus are equal to pi over 2.
Yeah, absolutely. Yeah, so let me just write this. So we get pi over 2 and arctan of 1 over x. To infinity to 0. Yeah, so if we use this thing here, the limit when x goes to infinity of f of x, that will be equal to c plus. Okay, that's that uses what's in blue above. And so through limit uniqueness, we get the result that follows. Get c plus equal to pi over 2. Again, through the same reasoning, it's the same reasoning at minus infinity. C minus is equal to minus pi over 2. And so if we come back to the actual question, which was find where arctan of x plus arctan of 1 over x is equal to pi over 2 and minus pi over 2, and we can conclude that it's r plus star and r minus star. So we conclude that any x on r plus star f of x is equal to pi over 2, and for any x on r minus star, f of x is equal to minus pi over 2. Which allows us to conclude on the question. Okay, we've solved that now. And what we can turn to is the following questions. So we're going to look at question B, which involves looking at where arc cosine of x plus arc sine of x is equal to pi over 2. Now again, if you've got a way of graphing functions in front of you. So either, I mean, Google does it, but if you've got a graphing calculator or something, have a look at what happens if you plot arc cosine of x plus arc sine of x.
Can you repeat the question?
Yeah, what we're going to look at is this question B here. And so to get some intuition on what we're going to try and prove, have a look at the graph of arc cosine of x plus arc sine of x. If you've got Google or something like that, you should be able to plot the graph of this function.
Well, even without plotting it, if it's always equal to pi over 2, it's going to be parallel to the x-axis.
We don't know. We don't know where it's equal to pi over 2 yet.
Okay, I thought. Okay,
yeah.
I thought this was okay.
No, yeah. Yeah, if you look at the exercise, we've got to prove the following equalities and find where they hold.
I would say 0 from the graph. No, actually, I don't know.
Well, what can you see if you look at the graph?
Well, it doesn't want to show up when I type arc cos x plus arc sin x.
Oh, okay. What you should see is this. If you get a, I suppose it depends on what graphing thing you use, because some of them are probably more or less happy with graphing this sort of thing. But you'll probably, if you manage to get something to work, if you have pi over 2 here, you'll have a function that's equal to, that's constant and equal to pi over 2 between -1 and 1. And then elsewhere, so you just have some sort of line there, and elsewhere you've got absolutely nothing. So that's due to the fact that arc cosine of x and arc sine of x are only defined on -1, 1. And then if you take the sum of the two, you're absolutely right, you get a line that's parallel to the x-axis. That's because the sum of the two is constant. And so we're going to try and prove that here. So we're going to prove that this equality holds for x between -1 and 1. So that's what we're going to try and prove. I'm going to say that show that this holds for x between -1 and 1. So let's have a look at that, and we're going to use similar techniques to question 1. In fact, this one will be much quicker to justify. So I'm going to define g of x as arc cosine of x plus arc sine of x. G is continuous on -1, 1. Okay, and G is differentiable. Where is G differentiable actually?
I would have said -1, 1.
Yeah, yeah. Do you take the bounds? Do you include them or not in your interval?
There's a right-hand limit at -1 and a left-hand limit at 1, but I don't know if that counts.
Yeah, you're right there. There's a limit, but the limit of the, if you take a look at the limit of the derivative at -1 and 1, you'll get something with an infinite slope. Sorry. So the differentiability only holds on the open interval. I think that's what we proved for arc cosine earlier. But what that tells us is that if we compute, if we take x on -1, 1 now, and we compute g prime of x. So we saw a minute ago, in fact, let's, so you've got arc cosine and arc sine. Here you've got the derivative for arc cosine that we proved a minute ago. So it's -1 divided by square root of 1 minus x squared. And arcsine squared is 1 divided by square root of 1 minus x squared. So we've proven those in class. And so if you add the two, you'll just get 0. So you get g prime of x equal to 1 minus 1 over 1 minus x squared with the square root. And you get plus the same thing. So that's equal to 0. And so what that tells you as a consequence is that g is constant on minus 1, 1, with that being the closed interval. If you look at your, I think that's in your notes. If I look for one of the last results you went over in this chapter, which is here. A function is constant on a closed interval when it's continuous. Continuity is really important here. If and only if f prime is equal to 0 on the open interval. So here, the fact that we can't derive right at the edge of the interval doesn't matter. You're still constant on minus 1, 1, with the key being continuity. So we know that the function is constant. And so we know that if we get one value for the function, then we've got all of the values. Do you know any particular value for arc cosine of x plus arc sine of x?
You can compute g of 0.
Yeah. We have g of 0 equal to arc cosine 0 plus arc sine of 0. And so what we showed in the first class is that arc cosine of 0 is equal to pi over 2. And arc sine of 0 as sine of 0 is 0. That's just 0. And so you get g of 0 equal to pi over 2. So you know your function's constant on a closed interval. We have one particular value. And so what we then get is, you know that the function is equal to that value on the whole of the interval. So you conclude that any x minus 1, 1, g of x is equal to pi over 2. So this here holds for x between minus 1, 1 with minus 1 and 1 included.
Kind of makes sense because cosine of x is equal to sine of pi over 2 minus x. But since here it's the inverse function, the pi over 2 is added before the doing arcsine.
Yeah, actually, that's a really good remark. Yeah, absolutely. That's probably exactly where it comes from. Yes. Yeah. Yeah. Now, all three of the other questions, so these three are all use exactly the same principle. As you can see, the next one still looks rather quite simple in the sense that these functions aren't that intimidating. The two last ones are a bit more intimidating. But we can have a look at arc cosine of x plus arc cosine of minus x, and what that gives us. So we want to have a look at where arc cosine of x plus arc cosine of minus x is equal to pi. And if you manage to get a graph of arc cosine of x plus arc cosine of minus x, you'll see that that function is equal to pi everywhere where it's defined, so on minus 1, 1. And so we can prove this. And it uses very much the same principles as above. So if we let h of x map to arc cosine of x plus arc cosine of minus x, we're going to show that that function is constant. So h is defined and continuous. On minus 1, 1. H is differentiable on the open interval. So -1, 1, but without including the bounds. So like this. Okay, so that's where it's differentiable. Now, if we take any x between -1 and 1, and we compute the derivative, so h prime of x, so it's arc cosine prime for the first one, so that's 1, or -1 rather, divided by square root of 1 minus x squared. And then we've got a composite derivative to deal with for the next one. So we're going to take minus x prime times arc cosine prime minus x. So we need to add that one. And we'll see that we'll get something that cancels out to 0. So minus x prime gives us -1. And that will cancel with the -1 of the arc cosine derivative. And to get h prime of x equal to 0. So h, as a consequence to this, is constant on -1, 1. And so again, we just need a particular value. So what value could we take here?
0 once again.
Yeah, absolutely. So as arc cosine of 0 is equal to pi over 2, we get h of 0 equal to pi. So you've got a function that's constant on the interval. You know one of the values on that interval. So in particular, we can conclude that for any x on -1, 1, but with the bounds included, not arc cosine, h of x is equal to pi. So again, this interval here holds for any x between -1, 1 with the bounds included. Now, as you can see, questions D and E are, well, I can tell you that they're the same idea. So here you've got a function that will prove to be constant where it's defined. And here too, if you take the difference between that and that, you subtract the two, you get a function that's constant. I think we'll leave these till the end of the week. So if you want to practice using the different principles that we use in this exercise and get some practice on derivation, you can try and look at these for like Thursday or Friday. I won't do them now because we've done 3 already. So maybe to finish this class, we'll look at something a little bit different. But yeah, questions D and E we'll do a little bit later in the week to give you a bit of time to maybe go back over this if there's anything that's puzzling you. Are there any questions on this exercise, on the things we've done so far?
No.
Okay. Okay. So we've done these 3 and we've got those 2 to do. So what we can do to finish today is take a look at one final exercise. It's on that will apply differentiability theorems to derivatives of functions. So derivatives of polynomials rather. So we're going to apply the different theorems that we've seen, so notably Rolle's theorem, to polynomials and prove various properties that will probably ring some bells from chapter 3. So that's what we can do now. Okay. So this exercise is going to be in two parts. The first one, we're going to look at a specific polynomial that's going to be explicit. And we're going to prove a certain property that we've seen in chapter 3, but we're going to prove it slightly differently. And then we're going to look at a variant of that with a slightly different polynomial and prove another property again. But first of all, what we want to do is tackle this question. So we're going to take this polynomial here. So it's x squared minus 1, x squared minus 4. So that's a polynomial function. And what we're going to try and do is, without computing f prime, show that f prime cancels out exactly 3 times on R and plot f. So what can we say about this object here? So it's f of x that maps x to x squared minus 1 times x squared minus 4. So what type of object is it?
A polynomial function?
Yeah, absolutely. So f is a polynomial. And it's of degree 4. So one thing that we know about polynomial functions is that they're C-infinite on R. Okay. So if we want to do anything related to derivation, etc., we're absolutely fine doing that on the whole of R. What can we say perhaps about, so what we want to look at is where f prime cancels out without actually computing f prime, but we want to show that f prime cancels out exactly 3 times on R, meaning that f prime sort of crosses 0 exactly 3 times on R. But what can we say about where f crosses 0?
1, 2, and minus 2.
Yeah, you got in fact you've got 4.
Sorry.
Yeah, you've got 4 real roots. We can rewrite f as follows. So we can rewrite f so that it's even more visible. F of x is equal to x squared minus 1, x squared minus 4. And if you just rewrite both of those terms, you get x minus 1, x plus 1, x minus 2, x plus 2. So f has 4 different real roots. So you've got 1, minus 1, 2, and minus 2. Now, what we want to do, so we've got all this information on f, but what we want to do is actually derive some properties related to the derivative of f. And one way that we can do this is using one of the differentiability theorems that we had. So it's Royle's theorem. If you have a look in your notes, it's about it's towards the end of this chapter. So it's there. So Royle's theorem tells you that if you take a and b, 2 different real numbers, and you take a function that maps from a, b to r, and if it's continuous, differentiable, etc., and if f of a is equal to f of b, then there exists some C in AB such that f prime of C is equal to 0. Okay, so this is a general theorem for functions, and it will allow us to work with our exercise to prove what we want. So if I just paste that here, okay. What we want to do is show that f prime for this f here is equal to 0 exactly 3 times on R. Now, can you see any way of applying Rolle's theorem based on what we've written above?
Well, we can take A equal to -1 and B equal to 1, and then do the other couples.
Yeah, absolutely. Yeah, that's exactly what we can do. So I'll just reorder this, the list of the 4 things. So you've got -2, -1, 1, 2. So if we look at the 4 different roots, for each of these roots, f of the root is equal to 0. So in particular, f of -2, for example, is equal to f of -1. And so if we apply Rolle's theorem with f, our polynomial above, we know that between -2 and -1, there's some value such that f prime of that value is equal to 0. And then, as was just said, we can apply that between -1 and 1 as well, and 1 and 2. And that will give us 3 roots for f prime. So we can work with Rolle to prove the result that we want. So let's first of all work on -2, -1. So we can apply Rolle's theorem on -2, -1. So f is C0 on that interval. That's the first thing that we can say. And the second thing is that f is differentiable on the open interval. Okay, and the third thing is that f of -2 is equal to f of -1 is equal to 0. So through Rolle, there exists, if we just copy the sort of statement and adapt it to our case, we'll call it there exists some C1 between -2 and -1, such that f prime of C1 is equal to 0. And as we said, we can also apply Rolle on -1, 1 and 1 to 2, and get, if we do that, I take this statement and just adapt it slightly, so I can write it twice. We can find some C2 between -1 and 1. And we'll get f prime of C2 equal to 0. But also you'll get, if you work on 1, 2, you'll get C3 between 1 and 2. And f prime of C3 will be equal to 0. And so our goal was to prove that f prime cancels out exactly 3 times on R. And what we get here is that if you look at how C1, C2, and C3 are constructed, you know that C1 is strictly smaller than -1, which is smaller than C2, which is smaller than 1, which is smaller than C3. So basically C1, C2, and C3 are definitely 3 different points. So F prime cancels out, or cancels, at least 3 times. On R. But we want to show that it cancels exactly 3 times on R. Can you see any way of justifying that related to polynomials?
If there was one more time, then there would be another root between, so where we could apply this theorem again. I mean, for example, if there was a 4th root, there should be for example, -3 to apply this theorem again.
Yeah, no, yeah, exactly. I see exactly what you mean. Yeah, but to justify that neatly, it's linked to the degrees of your polynomials.
The limit at -infinity is +infinity, and the limit at +infinity is also +infinity. So the derivative has to be negative from -infinity to some point, and positive from another point to +infinity. And so it has an odd number of zeros. Wait, yes.
Yeah, the issue with that reasoning is that there's nothing there to I think that with your first lot of reasoning, it would allow you to possibly prove the result through an absurd by showing that if you had an extra root, it would be absurd or something. But the basis for your reasoning would basically rely on the degree of your initial function. I think so. One way of sort of proving it quite quickly is that.
Excuse me.
Yeah.
I actually don't understand why we can't apply Rolle's theorem to the interval -2, 2.
You could. You could apply Rolle's theorem to -2, 2. You could even apply it to, for example, -2, 1, -1, 2. The thing is that if you say you apply it to -2, 2, then you'll get 1 point between -2 and 2, such that f prime of, say, call it C4 equal to 0. But the point that you get, so C4, could actually be C1 or C2 or C3 or some 4th point. We don't know whether it's a sort of a new point or whether it's one of the 3 that we've already found. Does that?
But
you wouldn't be able to write this, yeah.
But then how do we know that there are exactly like 3 roots and no more roots?
That's a very good question. All we know from what we've proven here is all we know is that there are at least three roots for f prime. But what we need to do is reason a little bit more to show that there are exactly 3. But what we have is that the degree of f is equal to 4. If we have a look,
maybe we can say that the degree of f prime is 3.
Yeah.
And so it has at least 1 root, but less than 4.
What's the maximum number of roots a polynomial of degree n? And the maximum number of real roots a polynomial of degree n with real coefficients can have?
N.
Yeah, exactly. So we're dealing with a polynomial of degree 3 for f prime. F prime belongs to R of x. Okay, we're working with real coefficients. So f prime has at most 3 real roots. So if you have a look, we have if you use the theorems that we had related to polynomials, f prime has at most 3 real roots. So what does this tell us if you combine both of the statements?
It has 3 roots and it can't have more.
Yeah, exactly. So what we can deduce from this is we conclude that f prime cancels out or is equal to 0 exactly 3 times on R. So in particular, there's no other point where f prime will be equal to 0. So we want to plot f for some reason. So the last part of this question, once we've deduced that, is to plot f. So we can give a rough graph of f with the reasoning that we've used so far. So we know that we've got 4 roots for f. So you've got 1, I think, 1, 2, minus 1, minus 2. And we know that the function's got exactly those 4 roots. So if you try and graph the behavior, damn it, you'll get something like this. So the points, in fact, where the derivative cancels out are here, here, and here. And those are the only places where the slope of the, so the derivative, sorry, is equal to 0. So the slope of the function is sort of flat like that and equal to 0. So it's a combination of Rolle and the fact that we've got real a polynomial with real coefficients of a certain degree. Is that exercise okay? Or this question rather? Okay.
Yes, I just want to say that my remark before that to use the Wahl's theorem again doesn't work. It could have an asymptote that's just below 0 and then it doesn't have any root. It still has a minimum.
Say that again.
So if there is a minimum below 0 and there's an asymptote just under 0, then there is no no additional.
Oh, I see what you mean. You mean if we shift this curve downwards and that it becomes below 0? Is that what you're saying? If
No.
this bit is no.
I mean, it doesn't. Maybe I can try to draw it, and
Yeah.
I can't.
Can you share your screen at all or not? It doesn't. No, I don't know if you can.
No, it doesn't matter. It was just to say that using Wahl's theorem doesn't work.
Yeah. Okay. Okay. Yeah. Okay. What we can do now is work with a slightly more general polynomial. So I think if you have your exercise sheet at hand, there's a mistake here in the what you're asked to look at, or what you're asked to prove at some point. But so here we've looked at an completely explicit polynomial, and we're going to look at a slightly different one here, and sort of show a principle that's almost a generalization of what we've just shown in a more specific case. So what we're going to consider is x squared minus 1 to the power n. So it could be x squared minus 1 or x squared minus 1 all squared, etc. And we're going to show you that if you, so this function is a polynomial, it belongs to C infinite space on R. So you can derive it as many times as you want without any issues. And so what we're going to show is that if you differentiate this polynomial k times, where k is somewhere between 1 and n, then you'll reach a derivative that's of the following form. So you get x squared minus 1, so this term here, to the power n minus k times rk of x, where rk of x will be a polynomial with k different roots, all located inside minus 1, 1. And so the reasoning for this will be a sort of generalization, I guess, of the reasoning above. It will sort of involve Rolle, but because we're working with a more general polynomial in a degree n, there'll be a little more abstract reasoning, I guess. So that's what we want to show. Do you have any idea about the type of method we could use to show this? So we've got n in n star. So we want to prove this for any k between 1 and n. So if we had to do all the calculations, it would probably be a bit of a pain. So there's a method that we can use that's a classical method in maths to prove this.
Maybe using roots multiplicity.
We will need roots multiplicity, yeah, but we can prove it by induction. So we're going to prove this. We're going to do an induction on k here to prove this statement. So we'll show first that G1 holds, and then sort of extend the proof to any k between 1 and n. So what we're going to show, we can show by induction that for any k between 1 and n, the following statement holds. So we call it ik. It's the fact that gk of x is x squared minus 1 times to the power n minus k times rk of x, where this thing holds. Rk has k different roots, all located inside minus 1, 1. That's our statement, including the thing that I've just copied and pasted. So if we want to prove this through induction, we first need to look at the initialization, or the base case. I don't know what you called it in Math 0. Let's call it the base case. So if k is equal to 1, if k is equal to 1, what do we end up proving, or what do we end up computing? We have k equal to 1, g of x equal to x squared minus 1 to the power n. So k equal to 1 equates to the first derivative of this. What's the first derivative of this polynomial?
(2x).
Yeah, that's a good start. So you get, it's a composite derivative. So you'll have the derivative of what's inside here.
I didn't see it was n minus k. Sorry.
Don't worry. So you get g prime of x equal to, so you get 2x times n times x squared minus 1 to the power, I'll write it underneath to give myself a bit more space. It'll be to the power n minus 1. So does this fit in with the form of the inductive statement? So it rewrites as x squared minus 1 to the power n minus 1 times r1 of x, where r1 of x is equal to 2 times n times x. And we want r1 to satisfy this property here. So it should have one root somewhere between -1 and 1. How many roots does this thing have here?
A single one at 0.
Absolutely, yeah. So R1 of x is a polynomial of degree 1 with a single root zero. So basically I1 holds. Okay. Now, what we want to do is prove that this now sort of holds for any k between 1 and n. So we're going to look at that and prove the inductive step. So let's have a look at the inductive step. So we're going to suppose that ik holds for, we're going to look at k between, suppose that it holds for k between 1 and n-1, okay, and that's going to be fixed. So it's sum k between 1 and n-1 fixed. So what that tells us is something on the kth derivative of g. So gk of x should satisfy the following. So it's x squared minus 1 to the power n minus k times rk of x. And in particular, we want rk of x to be a polynomial with a certain number of roots located a certain number of spaces. So if you look at the notes related to the exercise, rk is a polynomial. So you want rk to be a polynomial with k different roots, all between -1 and 1. Rk a polynomial of degree k with k different roots between -1 and 1. So basically what that means is that rk of x can be factorized as follows. So it's c times x minus some a1, x minus some a2, x minus some ak, with c is some value in r, and -1 is strictly smaller than a1, strictly smaller than a2, strictly smaller than ak, which in turn is strictly smaller than 1. Okay, that's the thing that we suppose, and that's the consequence on rk of x of the statements above. Now what we want to now do is have a look at what this means for the second, or the derivative of order k+1 of g. And one thing that we can do before going that far is just having a look at this here. How can we rewrite x squared minus 1?
X plus 1 times x minus 1.
Yeah, absolutely. Note that x squared minus 1 n minus k is equal to x plus 1 n minus k x minus 1 and minus k. So what we have is minus 1 is a root of multiplicity m minus k for gk, and 1 is a root of multiplicity m minus k for gk. So what does that tell us about minus 1 and 1 and their multiplicities for the k plus 1 derivative of g? If minus 1 is a root of multiplicity m minus k for gk, what can we say about if you derive one step further?
Well, it's still going to be a root until the n minus kth derivative.
It's still going to be a root, indeed. And so you can say that the multiplicity will be at least n minus k minus 1. It might still be n minus k, but it may be that you lose some multiplicity. So what we can deduce is the following. Minus 1 is a root of multiplicity at least m minus k minus 1 for gk plus 1, and we'll have the same thing for 1. And you'll see why we write this a little bit further on in this exercise. It's sort of a bit of a side note for now, but we'll need it a bit further on. So you've got a bit of information on gk plus 1, but it doesn't really help us yet. What we want to do is, if we sort of forget about this and the multiplicity of minus 1 and 1, we know that gk, so the kth derivative, writes as this first polynomial times a polynomial of degree k with all these different roots. And we want to have a look at what happens if you derive one step further. And so if we use the same reasoning as for question 1, can we get any information about the roots of the derivative of our polynomial by applying Rolle with these values here? For example, if we consider, if you use the notation a0 for minus 1 and ak plus 1 for 1, because it helps us a lot. If we have a look at what happens between a0 and a1 now, and we take this polynomial, we know that gk of a0 is equal to 0, gk of a1 is equal to 0, and the function is sort of C infinite between those two values, so we can apply Rolle, and we'll get some value b, for example, let's call it b0, such that the derivative of this is equal to 0. And we can go on further and further, and we'll get different roots. Okay, that's just applying Rolle like we did in the previous question. Okay, so if we apply Rolle, on aj plus 1 for each value j that's between 0 and k. We have gk is continuous on aj plus 1, and we have gk differentiable on the open interval and as aj and aj plus 1 are roots of the initial function, we have gk of aj equal to gk of aj plus 1. And so if we apply Rolle, there exists some bj in between the two, so between aj and aj plus 1, such that the k plus 1 derivative of g at the point bj is equal to 0. Again, if we do this for any k between 0 and k, with the boundaries included, what we obtain, we obtain k plus 1 different roots for the k plus 1 derivative. So you get b0 smaller than b1. B0 is between a0 and a1. And then you get b1 between a1 and a2. And right at the end, we'll get ak minus 1 smaller than bk smaller than ak. And remember that a0 is the notation for minus 1, and ak is a notation for 1. And so we've got a root here, a root here, a root here, and if you count them from b0 all the way to bk, you've got k plus 1 different roots. So b0, b1, all the way up to bk are k plus 1 different roots for gk plus 1. But what other roots do we know about for gk plus 1? If you have a look up here,
we also know that minus 1 and 1 are also roots for the gk plus 1.
yeah, absolutely.
Because, yes.
Yeah, go on.
If we derive gk, there will still be roots.
Yeah, absolutely. Basically, you know that when you're, if you think of the definition of a multiple root, you know that you're a root of multiplicity k. If you can keep deriving your function a certain number of times, and you're still a root. And so basically, when you derive a function, if you've got a multiple root, that value will still be a root of at least the same multiplicity minus 1 of the next polynomial. So that's what we have here. We know that minus 1 and 1 are roots of multiplicity at least n minus k minus 1 for gk plus 1. So if we write that here, we also have, using what's above, so blah, 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 minus 1 and 1 are roots of multiplicity at least n minus k minus 1 for gk plus 1. Now, what's the degree of gk plus 1? Yeah. One thing that we could note is that we have at least k plus 1 plus n minus k minus 1 times 2. And you can rewrite that as k plus 1 plus n minus k minus 1 plus n minus k plus 1, which, if I take that a little bit further, you'll see that one of the k plus 1 terms cancels, and so you've got 2n minus k plus 1 roots for gk plus 1. Now, what's the degree of gk plus 1?
I think it's the same thing.
Yeah, absolutely. So if we have a look at how to compute the degree, we have the following. The degree of g, if I use the degree of g initially, it was, so the polynomial was x squared plus 1 to the power n. And so in each x squared plus 1 term, you've got 2 roots, and that's to the power n. So you've got something of degree 2n, basically. And so if you have a look at the degree of g derived k plus 1 times, you get 2n minus k plus 1. So we've got a polynomial for which the degree is 2n minus k plus 1, and we've got at least 2n minus k plus 1 roots. So what does that tell us about what we were trying to prove? If we have a look at the inductive step, we know that minus 1 and 1 are now roots of degree exactly 2n, not 2, k plus 1. So we can write this form. Maybe I'll do that now. So we have all the roots for our polynomial. All of the roots for our polynomial. And what we end up with is, if we go back up, where is it? RK, no, gk plus 1 of x, sorry, is equal to x squared minus 1 to the power n minus k minus 1 times some rk plus 1 of x. And rk plus 1 of x is some c tilde times x minus b0 times x minus b1 with b0, b1, etc. All the values we found through Hol's theorem. We get up to x minus bk. And we've basically proven the statement that we wanted to prove, which is, I can't find it now, here. at step k plus 1. Okay, that's the inductive step, and the answer to the last question is really quite brief. So we know that if I just copy and paste this to stop going back up and down, we know that g derived k times is equal to x squared minus 1 to the power n minus k times rk, where rk satisfies some properties. What happens if you take the nth derivative? So if you take k equal to n and apply the formula above, what do we get?
Is the question how many roots r of x has? Interpretive question.
Sorry?
Well, what is the question?
What the question is, what is the, so, oh, I shouldn't have done that. In question B, we're going to look at g derived n times. And so if you apply this formula, what do you get for g derived n times? If you replace, yeah.
We just have
Yeah,
the
go on.
r of x, the rk of x. I mean,
Yeah.
rn of x.
Absolutely, yeah. If you set k equal to n, reduce the power n minus k, the x squared minus 1 terms disappears. So the nth derivative is Rn of x, with Rn of degree n cancelling at say a1 an with minus 1 smaller than a1 smaller than a2 all the way up to an, which then be smaller than 1, and so we basically get the following expression. We get Rn of x equal to some, let's call it b, x minus a1, x minus a2, x minus a1, an, sorry, with b and r. So we've got a product of order 1 polynomials, okay, and all of the roots, due to what we've proven through the induction, lies between -1 and 1, with -1 and 1 excluded. It's just a consequence of what's proven previously. So question B is just a consequence of what's proven above. The slightly more technical bit is question A, which relies on an induction, but it does use the same principle as question 1 of the exercise, where we can apply Rolle more sort of clearly. This question is slightly more abstract, but it's the same sort of principles. But yeah, that concludes on the exercise, and we can stop here for today. Are there any questions?
I don't have questions.
Huh?
I don't have questions.
Okay. If there are any, don't hesitate. But yeah, if there aren't any, we can stop there for today. Yeah, I'll get the notes to you when I can, and I'll see you tomorrow. I'll get an email to you tonight with the link for the Zoom for tomorrow's test. And yeah, have a good evening. And